So hello, this is homework. This is a probability and stochastic processing homework 11, question 2. So in these questions, it gives us three functions and it requires us to prove whether the three functions may represent an autocorrelation functions or a spectral density function. So as the first questions, we have proved that we know that the autocorrelation is real and even, and the spectral density is even and non-negative. So here we go. We can prove it in the following. For the first questions, fv equal to the a to the minus the absolute value of v. So firstly, we know that it is even as we take the minus value v into this function. We know that it is even. It's even, and then we take we make the v equal to omega. So we can obtain this formula, and the exponential to the power of absolute value of omega. We know that it is bigger and equal than 0. So from the definitions we have proved above, we know that it is both an autocorrelation and a power spectrum. So then we consider the second function. It's sin v square over v square. Firstly, it is also easy to say that it is even. So we omit the processing, and then we know that if it may represent an autocorrelation function, it must how to say that? It must make this line come true. So as r tau smaller and equal than r0. So we take the parameters into this function, and we know we can list the formula as this part. And as when t equals to 0, we can get the consequence is equal to 1. So the sin square v over v square is smaller than 1. It is accurate. So it's autocorrelation, and then it is easy to say that we make v equals to omega. So it is easy to say that this part is bigger and equal than 0. So according to the definition, we know that it can represent a power spectrum. Then we consider the third function. It's a uniform distribution. As when the absolute value with smaller and equal than alpha is equals to 1. we can sketch the graph like this. It depends on uniform distribution, and from the graph I sketch here, it's easy to see that it's even, and the R2 is smaller and equals than R0. So from the definition, it is autocorrelation, and we also can easily see that the spectral density is bigger and equal than 0. So from the graph I sketch here, so it is also easy to prove that it can represent a power spectral density.